Dear chief representatives from the regional authorities, chief representatives from national and also regional research institutions, dear colleagues. It is an extraordinary honor to welcome you here for the ceremony of the unveiling of the plaques for the two LIGOs and Virgo, named historical monuments by IEEE. Before passing the speech to my colleagues, I would like to say a few things, a few thanks, which also somehow reflect my views on the matter. I would like to thank, first of all, IEEE for the initiative to name us a historical milestone. I think by doing this demonstrates its deep intuition that scientific revolutions, as we believe is the discovery of gravitational waves, have a large impact on the ways that we inhabit the world, so even in the technology. Then I would like to thank the agencies, CNRS, INFN, NIKEF, that quite early were able to appreciate the visionary character of the proposal by Adalberto Giasotto, Alain Briet, and many other colleagues. We usually name only the two. And unshakably supported the project for 30 years. This is one of the key issues here. During many eras of skepticism and doubt about the possible outcome, having followed, if I can speak of myself, having followed this adventure from many positions during the last 20 years, I was able to witness first the strength and of character and persistence of the Virgo and Ego colleagues that insisted on doing that. And then the resilience of the scientific agencies in atmospheres of skepticism, uninspired false attempts of rationalization of resources that we all live in their support of the project. Obviously, the same thing happened in the US between our LIGO colleagues and NSF, and we're lucky about that. And we think that this is science at its best, which, contrary to a common view, science is not to produce certainty. It is how you manage and navigate in an atmosphere of uncertainty. And this boat was, I think, taken to port properly. And this is an important message, I think, for the times we're living. I would like also to extend, I only mentioned 3, but as you saw, these days we are 13 nations, and I would like also to have the same exactly comments for the other nations that participated starting 10 years ago. Third, I would like to thank our colleagues from the other continents, our LIGO colleagues in Kagra that worked in a close collaboration. I have seen through my involvements in many ways, many collaborations, international collaborations. This is a true international collaboration working as a single detector. And this is a big asset, I think, of this, although it is separated in different places. It's not a single place they work. And this collaboration also implicated other astrophysical observatories around the world in the Multi Messenger event, for which Virgo is nominally mentioned by the IEEE, extending the global character all over the world. I would like also to thank the present and previous Virgo spokespersons, and I would like to name them: Giovanni Losurdo, who will hear later, Jo van der Brand, Fulvio Ricci, Jean-Yves Vinet, you'll see in the film, Francesco Fidecaro, Benoit Moore, Adalberto Giazzotto, that started it all, as well as previous directors, Angelo Scribano, we have with us here, Filippo Metzinger said he could not come, and Jacques Collat, who is in France, and Federico Ferrini, whom we also have here. I think that their joint work brought us here, and they should mention by name. Last but not least, I would like to thank the regional authorities, as well as the heads of regional scientific institutions, whose large presence today honors us and makes us extremely happy, since their warm reception and hospitality facilitated the embedding of Ego and Virgo in the local societal and also STEM environment, increasing the many interdisciplinary synergies we were talking about it before of our science, which, just to name a few: geoscience, atmospheric science, ecology, informatics, multi-messenger physics. The region became the ecosphere of our initiatives, EU-funded or privately sponsored, on education, citizen science, and also art and science. Proving thus, once more, what I like to say, that a scientific revolution, as I said, we believe we are, it is always relevant to many notions of the antique notion of the cosmos, not only cosmos as universe, but cosmos also as Earth environment, and cosmos also as society and human character. So having said all that, I would like to pass the microphone to the co-organizer of the event, Bernardo Tellini, chair of the IEEE Italy section, who I have to say during the preparation, the long preparation, became a very good friend. So please, Bernardo.
Good afternoon. Thanks, Stavros, for this kind of introduction. Hello, everyone. I welcome you to this IEEE milestone dedication ceremony for the 3 gravitational wave antennas of Virgo and LIGO. As IEEE Italy section chair, it is a great privilege for me to be here today. And on behalf of the IEEE Italy section, I would like to thank you all for your participation. The IEEE milestone program honors significant technical achievements in all areas associated with IEEE and recognizes the technological innovation and excellence for the benefit of humanity. Please let me take this opportunity to introduce you to the IEEE Italy section and its rich milestone program. The association was founded in 1959, and 2 years ago we celebrated the 60 years from its foundation. Nowadays, the section is an association with more than 5,000 members, among which more than 1,000 students and graduated students. The first milestone for the Italy section was Volta's electrical battery invention, 1799, and it was dedicated in 1999. The other milestones are Marconi's early experiments in wireless telegraphy, 1895, dedicated in 2011. Enrico Fermi's major contribution to semiconductor statistics, 1924, 1926, dedicated in 2015. Dada's multiplier, 1965, dedicated in 2016. For studies on ring armature for direct current dynamos, 1860-1863 by Antonio Pascinotti, dedicated here in Pisa in 2018. Rotating fields and early induction motors, 1885-1888 by Galileo Ferraris, dedicated in 2021. Other two milestones are approved for the Italy section, dedications being planned. Giovanni Giorgi's contribution to the rationalized system of units, 1901-1902, and multiple silicon technology on a chip, 1985. This milestone is the 7th for the Italy section and the first one dedicated in 3 different regions of IEEE as a result of a great international collaboration. Thus, we are very glad and proud of this acknowledgement. Before concluding my speech, please let me thank the Minister of Research and University, Gaetano Manfredi, the President of Regione Toscana, Eugenio Gianni, the agencies, and all the speakers of today. A special thank goes to the IGO Director, Professor Stavros Katsanevas, and Dr. Vincenzo Napolano for their essential contribution to the organization of this ceremony. Please let me also thank IEEE and all the speakers who contributed to the pre-recorded part of this extraordinary ceremony, which will conclude with the unveiling of the plaque in live connection. Finally, I would like to express my personal emotion and send a special greeting to the family of Professor Adalberto Jasotto. Once again, thank you all for the time to join us today. Thank you.
The president of the region will come a little bit later. So we continue with Marco Pallavicini, president of the IGO Council.
Thank you, Stavros. It's, of course, I'm very happy to be here to host this event. Of course, I join the director in thanking IEEE Italian section for having proposed this. This is a milestone, and a milestone measures the road you have done, but also the one you have ahead. It's both. An enormous amount of work was done to achieve these fundamental results. Of course, the discovery of gravitational waves is a milestone of science. It took 100 years, an enormous amount of energy, of money, of faith to keep on with this enterprise. Of course, this was done first of all by the Virgo collaboration, by the scientists, by the people, but also by the institutions. And I would like, of course, to recall that this is an enterprise founded by an Italian and French institutions, INFN and CNRS. But I am happy to say that this is the first official event in which a third institution, which is NICEF, is officially part of IGO. So on behalf of the council, I thank IGO for joining, NICEF for joining, and of course, I hope that for the future, more countries will join, because as I said, the milestone we have reached is important, but we have a long way to go to exploit this new science. It took 100 years to discover gravitational waves, but this is a very young science. I think it's easy to predict that a lot of discoveries will come in the next years with Virgo, first of all, and this will be the task probably of the next 10, 15 years, but hopefully, and we are dreaming for another important detector, which will be Einstein telescope that we started to develop. And of course, we dream that in maybe 10 or 15 or 20 years from now, another plaque will be built. We will put somewhere for the important discovery of Einstein telescope. But now it's time to really thank everybody for this milestone, which is a crucial one. And I think that now it's time for the 3 presidents to speak about the role of INFN, of CNRS, and NICEF right now. So thank you very much, Stavros, for this, and thanks to all for joining.
Is the connection with Renaud Pain on? Or is it too early? Because we started a little bit earlier.
Hello, I am connected. Can you hear me? I'm not sure if I can start now. Please, someone tell me if I can start. Okay. Okay, thank you very much. So, good afternoon, everyone.
Yes, we
I'm
can.
not sure if I can
do you hear us?
start now.
Do you hear?
Please,
Can you hear us?
someone tell me if I can start. Yes, okay. Good afternoon, everyone. Not sure I can start now. Okay, let me start. Thank you very much for giving me the opportunity to say a few words on behalf of IEEE, the French National Institute of Nuclear and Particle Physics. So at first sight, it may sound a bit odd to some of you that an institute doing research in nuclear and particle physics has any connection at all with gravitational waves. And of course, this is also true for INFN and NICF, you'll hear later on. Since after all, gravitation is totally negligible when it comes to nuclear or even weak interaction. Also, particle accelerators have nothing to do with laser, although this may happen someday and maybe not so far away. But particle detectors are also not really at work here, even accounting for the fact that photons are, of course, particles, as we all know. Now, the real reason I think, and part of it may be from theory itself, which of course aims at connecting all forces. Now, the real reason I think is people, actually. So physicists, engineers, and science managers who were all convinced that Einstein was right and that gravitational waves exist. And they all boldly embark in a journey that would last more than 30 years, as Stavros mentioned, and is still going on. So I really like to take the opportunity of this celebration to mention a couple of names of people who were instrumental in France to get this project approved and going. Now, of course, many people and many more have been involved, and many were key in bringing this project to success. So I really apologize in advance for picking just a few names. So let me start. Let me start by saying that CNRS, with IEEE as a lead institute, joined this adventure in 1993 when the Virgo project was approved following the now famous Fleury report from the name of the particle physicist Patrick Fleury, who was at that time chaired this committee of about a dozen of eminent physicists, scientists, who had been asked to evaluate the Virgo project. Now, this committee, after careful examination of many scientific and technical aspects, and also several visits of labs in Europe and actually in the US as well, recommended that France invest in the detection of gravitational waves using the technique of gravitational wave interferometer. So this was in 1990. Now, by the way, they estimated the cost of this work, of this project, to be 325 million French francs, 1990 French francs, and also a duration of construction that would last 5 years. Now, 325 million French francs is almost exactly 50 million euros, which for a duration of 5 years actually amount to 10 million euros a year, which happens to be about the yearly LIGO budget today. So just a coincidence probably, but I think it's worth mentioning. So they were, in a sense, right about this, the yearly budget of LIGO, but of course they were a bit optimistic about the time it would take to make it work. But this is another story. So Soon after the Virgo project was approved by CNRS and INFN, construction began in 1997 in Pise, here at this site where this IEEE milestone plate will be installed soon. So back on names, I'd like to mention Alain Briet, who of course was a key person in France when it comes to lasers. Together with Thibaut Damour, a French theoretician, these two were awarded the gold medal of CNRS in 2017 for being key in discovering the gravitational waves. Speaking of CNRS, whose support was absolutely essential during the many years that it took to achieve the needed sensitivity, there were times, as Stavros already mentioned, where some people were expressing doubts on the feasibility of the experiment, and some even wanted to shut it down, considering it cost a large cost. So on this, I'd like to mention the name of Catherine Bréchignac, who has been Director General and then President of CNRS at those key moments where Virgo needed strong support from CNRS. Let me finish by mentioning Jean-Marie Markowski. His name may be less known, but he's been a key person in developing and fabricating the mirrors, which are so important for these antennas to achieve the desired sensitivities. Jean-Marie Markowski founded and directed for many years the Laboratoire des Matériaux Avancés, LMA, in Lyon, where not only Virgo mirrors, but also LIGOs 1 and nowadays Kagras 1 are being coated. People say that LMA makes the best mirror in the world. This is a truly impressive achievement, and we are very proud of IEEE at IEEE to support, and we will continue to support strongly this exceptional lab. Okay, so far for names. Oh no, almost forgot one. If you allow me, I'd like also to mention another person, and it is our host today, Stavros Katsanevas, who, when he was IEEE Scientific Director for Astroparticles and Neutrinos, strongly supported, with all his conviction, and he has a lot of conviction, you know that, he strongly supported the Virgo project. So thank you, Stavros, and on this I will finish. Thank you very much. Thank you again, and congratulations to the teams that have achieved such an impressive discovery. Thank you very much.
Thank you very much, Ronald. So now we continue with the INFN president.
Thank you, Stavros. Thank you, everybody. I'm very happy to be here as representing INFN, the National Institute for Nuclear Physics, who made a very big, important investment in this field. I think this is a very beautiful history, in my opinion, for the science. An history which started something like 100 years ago, and started as usual with a theory, the theory of general relativity by Albert Einstein, and finished after 100 years with the discovery of gravitational waves. In between, many things happened. And in order to achieve this goal, so to detect the gravitational waves and to have official recognition, the Nobel Prize and so on, in order to achieve this goal, as usual in science, you need a lot of things. You need, first of all, visionary people. And I would like to recall Adalberto Giazzotto. Without him, this would have never been possible, as Albert Einstein thought at the beginning when he made the prevision of gravitational waves. He didn't think it was possible to detect these waves. And after some years, you have a visionary person as Alberto Giardotto say, okay, it is possible. Let's try to make this project. And then you need an institution or some institution like CNRS and INFN, which are believing in the project and make a huge investment in terms of money, in terms of credibility, of science, and start to build up an infrastructure. And this is another important step because usually it's difficult to find institutions which are able to invest in infrastructure. And I think I'm proud that INFN is on opposite side. So infrastructure for us is really a central business. So we have our national lab in Frascati, Legnaro, and Catania. We have the famous underground lab in Gran Sasso, and we invested in this infrastructure in Cascina for building up IGO. And then you need the people, the scientists. Without them, again, it is impossible to reach such important goals. And of course, you have to face many difficult moments. So you need the courage, you need determination, you need to be concentrated on the goal. So after this period, why it took then after the proposal many years to reach the goal? Because in order to reach this goal, you need to develop cutting-edge technologies. So in the history of science, every discovery, experimental discovery, has been made because in this particular field has been developed cutting-edge technology. If you think at the beginning, Galileo or Tycho Brahe were able to describe the motion of the planets because they developed lenses of with a new technology, and it was possible to measure the position of the planets in the sky with a very big precision. And this was the same on a different scale. So in order to detect the gravitational wave, we have to develop cutting-edge technology, the suspension, all the things which has been used in IGO. And this is important, and is very important, the achievement and the recognition we had from IEEE, because it recognizes this part, which in most cases is neglected. So you make a big discovery, so scientists are great and so on. You neglect the fact that you have developed this technology, and this technology will be used on the society after 10, 20 years, or whenever the society will be ready to exploit the technologies. So I would like really to thank IEEE for this milestone, for this recognition, because it's a central point of all scientific enterprises. And I would like to close my remarks by thinking to the future. So we have discovered gravitational waves. Now we have to upgrade Virgo. Virgo++ is on the way. And in order to improve the sensitivity of the detector. And again, the technology is a central role in this. But then we have also to think to the next step, so the next gravitational wave detector. And we are proposing Einstein telescope, and I hope that all the expertise which has been developed here will be used and will be an important milestone to start the new project. And I hope that starting, if we think back, we started 100 years ago with a theory, and now we end up with a discovery, opening a new field, the multi-messenger research in astrophysics. So exploiting not only gamma rays, not only the light, but also gravitational waves in order to understand our cosmos and the universe. So I think it's the end of a great journey and the starting point of another one. So thank you very much. Thank you, Stavros. So,
and the next step is it's Dan Belvelsen
I
Director
think
of
it's
NICEF.
the end of a great journey and the starting point of another one. So thank you very much. Thank you, Stavros.
So good afternoon, dear representatives of IEEE and dear colleagues. Thank you for inviting me to be present in this celebration, even though at a distance. And I wish I was able to travel to Italy to join you and to witness in person this IEEE milestone celebration and recognition. However, unfortunately, the current pandemic doesn't allow me to travel, so I like to keep it short, but I would nevertheless like to share a few points with you. I represent NICEF, and as you may know, NICEF is a partnership between the Netherlands Organization for Scientific Research and our universities in the Netherlands, 6 in total, all over our country. And as director of NICEF, I witnessed the enormous boost in the field of gravitational waves over the past year. We joined the adventure of gravitational waves only relatively recent, some more than 10 years, long after INFN and CNRS had the vision to go for it and already started. But although we entered the game late, we enjoyed every moment of it. NICEF has produced significant instrumentation for Virgo, and we are involved in various upgrades programs of the antenna, notably on Newtonian noise cancellation, frequency-dependent squeezing, and controls. And I like to thank LIGO for being so open to our contributions and the fact that we are able to help in increasing the sensitivity on the instruments. So students and staff from our universities connected to NICEF are directly exposed to this research and are looking forward to the next level of more sensitive data in the coming years. Let me mention here one name of a colleague, our most respected senior physicist and driving force of gravitational waves at NICEF, Jo van der Brand, who actually took us to Virgo, and who also became spokesperson of Virgo in 2017. And with the first detections of gravitational waves, we entered a new era of exciting multi-messenger science. It's already mentioned by speakers before me. The prospects of this field are so promising that also the community in the Netherlands is growing rapidly. Our universities established new research groups, and the gravitational wave group is now the largest at NICEF. We should not forget the ties with industry and small companies to tackle all the challenging barriers for new detector technologies. And as Marco already mentioned, I'm very happy that recently NICEF has become a formal member of IGO, strengthening the international collaboration on gravitational wave research in Europe. I hope indeed that also that other countries will soon join as well. And this afternoon I saw a picture of Stavros raising the Dutch flag on the Virgo side, and I'm very proud of it. And I hope that it will stay there for many years to come. And looking toward the future, the ambitions of NICEF and also our colleagues in this field are high, as we foresee a rich and deep future of this research with an exciting science agenda. Together with INFN, we are coordinating the preparations to construct the next generation Einstein telescope. This dream project is on the drawing table with one scenario that it actually will be constructed at a border area between the Netherlands, Belgium, and Germany. And the coming years will show how realistic these plans really are and if we have political support. We are working on it. In the meantime, the Netherlands, Belgium, and Germany have started to construct the ET Pathfinder, a fully operational R&D facility to test and optimize the instrumentation for the Einstein telescope, irrespective of its location. And I like to say that the leadership with Stefan Hield is in excellent hands, and I'm sure you will hear more about the ET Pathfinder in the coming years. But coming back to Virgo and LIGO, I really like to thank Stavros Katsanevas for this dynamic and energetic leadership of IGO, and also for organizing this event. I like to thank INFN and CNRS for the vision and for the continuous support and for having us joining in the IGO Council. This IEEE milestone ceremony is a reward that fully fits its highly inspiring and challenging research. We as NICEF are proud to be involved in this scientific and technological quest. So let me keep it with this. I wish you all a good and happy continuation of this celebration in these difficult times. And I hope to see you all soon in real life again. And please stay healthy. Thank you. Quest. So let me keep it with this. I wish you all a good and happy continuation of this celebration in these difficult times. And I hope to see you all soon in real life again. And please stay healthy. Thank you.
Thank you very much, Stan. Now let's go to the scientists that do all these marvels. We will start with Raffaele Flaminio, who has a long tradition of contributions. He was among the first commissioners, and he was deputy director, scientific director at IGO, was head of LMA, and now is the project leader of Advanced Virgo Plus. So please, Raffaele.
Thank you, Stavros. So today I would like to talk about a journey in time, not the journey that the gravitational wave traveled for 1 billion years to arrive to our detectors, but more of a human journey of the scientists that traveled for many years to open this new field of gravitational wave astronomy. And in particular, I would like to talk about the contribution that the Virgo collaboration gave to this endeavor. The detection of gravitational waves has been a very long process. It took 60 years between the time Joe Weber in the United States built the first gravitational wave detector and the time we saw a first gravitational wave here at Virgo coming from the fusion of two neutron stars, which then led to the first identification of a new star emitting light at all wavelengths. It was very, very long, so long that at some moment we actually doubt that we could arrive at the goal one day. The scientists of Virgo have given an important contribution to this result, and here I want to remind some of these contributions. And first of all, it has already been said, but I want to repeat it, it's about the laser. In the mid of the 80s, Alain Brillet proposed to use a solid-state laser emitting infrared light. It was an unconventional choice. Everybody was using visible light for these detectors. Alain underlined that these lasers were more efficient, more stable, that the infrared light was easier to use. And since then, everybody in our field has adopted this solution. This was an important contribution. Another one was about the mirrors. In the same periods, in the mid of the 80s, Jean-Marie Markowski, who was a research engineer at CNRS, was building a small mirror like this, 100 grams, for the industry. And Alain Brillet approached him and asked him to build much bigger ones, 40-kilogram ones, much better quality, for gravitational wave detection. Jean-Marie was crazy enough to accept the task. And from there, the laboratory of advanced materials in Lyon was born. Nowadays, that laboratory produces the mirrors for all detectors of gravitational wave on Earth, not only Virgo, with which we started, but also in the United States for LIGO and for Kagra in Japan. Since I'm talking about Japan, it reminds me on one of the first kind of international, very international conference of this field, the first TAMA workshop. At that workshop in the middle of the 90s, Barry Barish, who was then one of the Nobel laureates, highlighted in his closing remarks one short paper presented at that conference by Benoit Moore, where Benoit was insisting on the importance that all these detectors should be able to talk to each other, use the same data format. That was the beginning of the so-called frame format, the data format that we still use and that everybody now is using for doing this physics. That was also a contribution for Virgo, from Virgo to this endeavor. And last but not least, of course, I have to underline the contribution given to this field by my supervisor, Adalberto Giazzotto. When I joined his lab in 1990, Adalberto had just built the first two super attenuators, these gigantic seismic isolators. And he asked us, me and our students, to hang an interferometer to this superattenuator and try to see the seismic noise filtering through the superattenuator to the suspended masses. And of course, we failed. We couldn't do it. And then we try again with initial Virgo. We hang initial Virgo to this superattenuator, and still we couldn't see the seismic noise. And same thing with advanced Virgo. Superattenuators are still in use. They will be used for advanced Virgo Plus, and they are already considered building blocks for the next generation, for the Einstein telescope. For this, I finished. I thank you for your attention, and I apologize for those that I couldn't mention the work because of the limited amount of time. And once again, I would like to thank Adalberto for giving me the opportunity to participate into this journey. Thanks.
Thank you very much, Rafael. And then we continue and end before the arrival, hopefully before the 5:30 of the regional, with Giovanni Losurdo. Giovanni Losurdo, I have to say very fast, was also among the people that worked on the superattenuator. He was the project leader of Advanced Virgo, the detector that finally saw gravitational waves, and he's currently the spokesman of Virgo.
Thank you, Stavros. Maybe I can remove this. And thank you, everybody, for being here with us. I stand here representing the Virgo collaboration, a community of more than 650 physicists, engineers, technicians, which includes also many people of LIGO from 13 countries, a community which has played a key role in achieving this milestone. And I would like to say a few words about the meaning of today's ceremony. There is not one meaning, there are many. First of all, we celebrate today a great scientific discovery, a discovery which had already an extraordinary impact on science. We celebrate also the scientists who have been able to see further, the ones who, with their scientific vision and dedication, have managed to achieve something unthinkable. Among them, I want to mention Adalberto and Alain. We celebrate all those scientists and non-scientists who, in many different ways, have contributed over the years to transform a concept of a project into an experiment that is playing a key role in epochal discoveries. We celebrate the funding agencies, which took risks by investing in a program very different from the mainstream, the CNRS, the NFN, and later NICEF. We celebrate the technologies which made it possible to make such a sensitive detector and all the people who have pursued their development. However, there is something more, something that makes this milestone so special. We are not celebrating today the end of a journey, but the beginning instead. We are at the dawn of a new adventure of knowledge in ways never experienced before. We have new detectors. We have a new messenger, the gravitational waves. We are learning to decipher this message along with other cosmic messengers. What we have learned in just 5 years from the first detection till today is amazing. We have been able to listen to a black hole, to understand how a gamma ray burst is born, how fast gravity runs, how heavy elements are formed, such as gold or iodine, which is essential for life. We even discovered black holes, which shouldn't have existed. As Galileo did, we keep improving our instruments in order to see further and further, but we are already looking beyond to a third generation of detectors that will allow us to observe the universe when it was still very, very young. To this extent, we have an ambitious project to carry out, Einstein Telescope, a project born and raised in Europe, which aims to be one of the main European research infrastructure in the next 50 years. A project that will allow us, through gravitational waves, to crucially contribute to the understanding of that 95% of the cosmos that still remains dark. Today, therefore, we celebrate the beginning of a new long journey through the new window that Virgo and LIGO have opened on the dark universe. A journey that begins in a very critical historical phase, while we have to face unprecedented crises a pandemic that is costing millions of lives and is having a tremendous impact on social relations, on the educational system, on the economy. And the climate change is time to produce a substantial transformation in our way of life. And to cope with them, we count on the contribution of science, which is already providing answers on the pandemic at a speed unimaginable, even in the recent past, proving once again to be a vital necessity for the society and for each individual. But what does all this have to do with the universe, with black holes, with the spin of the graviton? It's our thirst of knowledge, the innate drive to look for a simple reason explaining at the same time the smallest and the biggest things we observe. This is the fundamental engine for finding solutions even to contingent crises. As scientists, we are constantly confronted with the unknown, but we take up the challenge of composing, piece by piece, the mosaic of knowledge, and whenever we find an answer, new questions arise from it. It is a continuous challenge in which we find the capacity to know the essence of our human being, beings that are capable of perceiving their own smallness in front of the immensity of the cosmos, while at the same time daring to face the challenge of understanding nature. So, in this spirit, we received this award today, and we are grateful to IEEE, convinced that in the coming years and decades, we will contribute to reaching new milestones for the science and for the society in which we live and operate every day. And thank you for your attention.
So I thank all the speakers for really very short and to the point presentations. So we have 13 minutes before the streaming of the international event. I don't know whether whether outside the coffee is ready. It's ready. So if you want to take a short, I mean, it's normally we don't introduce coffee here, but let's make it. It's the pandemic. Let's make it convivial. So please feel free to go out, serve yourself something, and come back for the beginning. And then when the president of the region comes, we try to arrange a short visit to the black. So for those of you that will have to leave before. Okay, so please be back in 12 minutes. Well, a little bit later, it doesn't matter. Marco. Let me tell you something. I should tell you something.
Hello, everyone. I welcome you to this IEEE Milestone dedication event. I'm happy to say that we have attendees from all over the world joining us, including Pakistan, Indonesia, Canada, India, Australia, and Panama, from countries all over Europe and all across the United States, and from many other parts of the world. This is great, so let me give you a big, wide welcome. Now, some of you might be wondering, what in the world is IEEE? And what in the world is an IEEE milestone? You may have had a chance to answer these questions by exploring our website at gwamilestone.com, or you may already be a longtime IEEE member, such as myself. Our IEEE President-elect will be talking about some of these points following my opening remarks. But very briefly, let me say that IEEE is a worldwide organization with about 420,000 members who are engineers and scientists, and we help make the world go round. IEEE milestones honor the most important of these endeavors, and they teach us the story of how these major accomplishments came to be. Indeed, our program today will discuss the astonishing prediction about the nature of gravity made by Albert Einstein while a professor at the University of Berlin in 1916, and which was proven for the first time 99 years later. In case it doesn't already show, I love history. I've learned a lot of the stories behind many of the astounding accomplishments while working on over a dozen IEEE milestones over the last 10 years. And I've been lucky to be able to learn from some of the brightest people on Earth. I need to give a big thank you to the team members with whom I've been working on this dedication event. This includes Will Robinson, who's IEEE USA Vice President of Government Relations, and with whom I rendezvoused in Glasgow, Scotland back in 2019 in order to get this milestone approved by the IEEE History Committee. As you can imagine, a learned team from around the world must first judge a milestone to be historically significant and must also ensure that the citation as cast on a beautiful bronze plaque is factually correct. Today, we're going to hear about the historical significance of how 3 massive antennas in both the US and Italy were able to confirm that prediction of Einstein's. As part of my love of history, I've been reading a book entitled Endless Frontier, which chronicles the critical role of scientists and engineers working at research centers and universities such as MIT and Caltech during World War II. Their success forged an alliance of the government with schools and research centers across the country, and this led to the creation of the National Science Foundation in 1950. The resulting government funding of scientific research has led to advances in computing and communications, including the ability for all of us to come together in cyberspace for today's gathering. As you will see from our series of speakers, such alliances have borne amazing fruit, not only in America, but also in Europe, Asia, and elsewhere in the world. So not only do we have attendees from around the world with us today, but our speakers are an important international group of scientists, as well as dignitaries from organizations that provide essential funding for scientific research, leading to benefits for our populations and a better understanding of our universe. While it's unfortunate that we can't be together in person for today's event, our audience today is much larger than the number who would have attended the 3 separate events that were originally scheduled for last summer. Instead, here we are, all together from around the world at a single event. I must thank a few more people for their work in making today happen. Our core team consisted of Will Robinson, who met with me in Scotland, and who wrote the successful milestone proposal with critical help from Rich Abbott of Caltech and LIGO. Matt Francis has been our IEEE Region 5 coordinator for the sections near the Livingston LIGO site. We've also had tremendous help from Bernardo Tellini, who is a professor at the University of Pisa and who has served as our primary European IEEE contact. Bernardo enlisted the help of Stavros Katsanevas, who is a professor at the University of Paris, a director of the European Gravitational Observatory, which hosts the Virgo antenna in Italy, a past director of the Laboratory of Astroparticle Physics and Cosmology in Paris, and also a deputy director of the National Institute of Nuclear and Particle Physics of the French funding agency CNRS. I need to give a big shout out to the team at IEEE USA that allowed today's event to be transformed from a slate of international participants to the reality of this online event. This includes our videography and rendering team of Jonathan Cho and Corey Ruth. In addition, we thank Aline McNall for being our liaison with the National Science Foundation, and Kate Duncan, who is the 2021 IEEE USA President. I also want to thank the IEEE Foundation and its Executive Director, Karen Gallucci, for its funding of the activities of the IEEE History Center and its Milestone program. Thank you also to the IEEE section officers in Baton Rouge and New Orleans, Louisiana, and Richland, Washington, for soliciting proclamations and video recordings from Richland Mayor Ryan Luxon and Livingston Mayor David McCreary. Thanks also to Dr. Sherry Nguyen for her work with the Washington Governor Jay Inslee, and to Will Robinson for his work with the Governor and Lieutenant Governor of Louisiana. You will hear some of these dignitaries during our program, and also find proclamations and videos from them posted on our website. Finally, thanks to the IEEE Consultants Network of Silicon Valley, of which I am a director, and to Sherry Nguyen of the UNESCO Washington State Center for their funding of mementos, which honor the milestone and the 3 observatories. Our first speaker is IEEE President, Dr. Ray Liu. At the University of Maryland, College Park, Dr. Liu is a distinguished university professor and the Christine Kim Eminent Professor of Information Technology. Dr. Liu is a fellow of the American Association for the Advancement of Science and of the U.S. National Academy of Inventors. He is also an IEEE Fellow for contributions to algorithms, architectures, and implementations for signal processing.
Thank you, Brian, for that introduction and for your kind invitations to participate today. Hello, everyone. Thank you all for joining us today for this very special IEEE milestone dedication ceremony for 3 gravitational wave antennas. As 2021 President-elect, it is my pleasure to take part in these celebrations. This event is in recognition of the detection of gravitational wave as predicted by Albert Einstein's 1916 theory of general relativity, as well as the fundamental achievement of the direct measurement of gravitational wave. I would like to thank everyone for taking the time to participate in this international ceremony. It is quite a feat to simultaneously dedicate flags at 3 unique locations around the world. By celebrating the pride and prestige of our professions, we demonstrate how engineers, scientists, and technologies contribute to our global community and have helped to build today's technologically advanced world. For those who are unfamiliar with IEEE, we are the world's largest technical professional organizations. IEEE's core purpose is to foster technological innovations and excellence for the benefit of humanity. IEEE is a world-leading publisher of trusted, high-quality technical information, a principal organizer of international conferences, a value provider of educational material, and a developer of widely used international standards. Our nearly 420,000 members across 160 countries are vibrant, diverse engineering and technological professionals who are committed to elevating their professional image, expanding their global network, connecting with peers locally, and giving back to their community. Dedicating an IEEE milestone take tremendous effort, and the member across the numerous IEEE regions are to be commended for their generous gift of time in bringing this dedication to completion. As the detection of gravitational wave had become a global effort, so was the planning and organizing of this international ceremony. In particular, I would like to thank my IEEE colleague, Baton Rouge Section Chair Don Covillian, New Orleans Section Chair Chen Wong, Richland Section Chair Leo Fitzfield, and Italy Section Chair Bernardo Terlini. I would also like to thank the core program planning team, led by Brian Berg, who is the Region 6 History Chair and Milestone Coordinator, a member of IEEE History Committee, and a Director of the IEEE Consultant Network of Silicon Valley. Some of you may be asking, what is an IEEE milestone? The milestone program honors significant technical achievements in electrical, electronic, and computer engineering and the associated science. Funded by donation to IEEE foundations and administered by our History Center, the program recognizes great moments throughout our world's long history of technical innovations. The program began in 1983 as part of IEEE's centennial celebrations. Today's milestone is our 213th worldwide. It is the first milestone for both Baton Rouge and Richland section, and the 7th for the Italy sections. It is also the first milestone to be dedicated in 3 IEEE regions. For Region 5, this is the 13th milestone, the 29th for Region 6, and the 51st for Region 8. IEEE milestone help to increase the public's understanding of the contribution of society made by electrical, electronic, and computer engineers, and the stride made by countless technologies as they sought to advance technology to benefit humanity. They are symbols around the world of how electrical engineering and computing have helped to build the modern world and bring people closer together. It is my privilege to recognize these pioneering events and the people behind them. They serve as landmarks in the progress of technology and in the progress of civilizations. I am honored to be a part of these celebrations. I would like to thank you all again for joining us today, and I applaud all the organizers of this extraordinary, inspirational program. Thank you.
We're pleased to have with us today the Honorable Sethuraman Panchanathan. He is a computer scientist and engineer and is the 15th director of the U.S. National Science Foundation. Dr. Panchanathan is also a fellow of the IEEE, an honor he received for his contributions in compressed domain processing and indexing, in visual computing, and communications. The NSF first started funding LIGO feasibility studies in the 1970s. LIGO is one of the most ambitious projects ever undertaken by the NSF. The NSF's appreciation of the need for a far-sighted perspective when it comes to complex scientific research and engineering is on display in today's event. As such, today we salute the absolutely essential role that NSF funding has played over the last 70 years. Dr. Panchanathan will now share his thoughts about the extraordinary achievements that are a direct result of the NSF's perseverance in this program.
Good day to all of you. I am Sethuraman Panchanathan, and I'm so honored to join you today on behalf of the National Science Foundation in recognizing the amazing accomplishments and discoveries of the LIGO and Virgo collaborations. A century after Albert Einstein first predicted the existence of gravitational waves, they were detected emanating from the collision and merger of two black holes in a cosmic event that occurred approximately 1.3 billion years earlier. This amazing feat was made possible by sustained investment, dedication, world-class research, and strong collaborations across our country and around the globe. It took decades for the vision of the early pioneers in gravitational wave science to become reality. It also required sustained support from governments and academia. From the first awards in the 1970s to the construction of the antennas in Livingston, Louisiana, and Hanford, Washington, where these milestone plaques will commemorate this achievement. The National Science Foundation invested more than $1 billion over 4 decades. In fact, LIGO was the first of our agency's major research equipment projects and highlighted NSF's unique role and ability to fund the high-risk, high-reward research infrastructure that propels science forward and transform our future. But maybe most importantly, it was the product of the curiosity and ingenuity of those initial visionaries and 1,000+ scientists and engineers across more than a dozen countries who worked as a team to tackle a grand challenge. LIGO's success was possible because of superb engineering in many of the areas of importance to the IEEE, such as photonics, low-noise electronics, digital signal processing, and servo control systems. Among the prestigious awards associated with LIGO is the 2017 Nobel Prize in Physics, awarded to Ray Weiss, Kip Thorne, and Barry Barish. It is an honor to be able to thank them today, once again, for their contributions to science and human knowledge. The discoveries did not end with that initial detection of gravitational waves on September 14, 2015. In fact, the LIGO and Virgo collaborations have gone on to be prolific in producing groundbreaking results and changing the way we view the universe. We have opened a new window through which to observe, and it has allowed us to see what could not be seen before. For instance, there have been numerous detections of black hole mergers, including black holes with masses that are difficult to explain. We have also observed the merger of 2 neutron stars, answering questions about the origin of the heavy elements in the universe. I'm so excited for what the future holds. NSF has continued to invest in the future of LIGO and the facility's ability to study gravitational waves and their origins. Equally important, is the investment in the generation of scientists and engineers that have been inspired by your work and that will one day build upon it. That is why strong education and outreach efforts around these accomplishments and the science that underpins them is so critical. The strong partnerships between the LIGO facilities, academic institutions, and the states of Louisiana and Washington are central to this endeavor. I'm so pleased to see the broad partnerships that have formed between academia, government, and other organizations to expand the educational impact of LIGO. For example, the partnership with Southern University is an excellent example of how we can broaden the reach and impacts of these world-class facilities. I'm also thankful for the commitment the state of Washington has made to support educational initiatives at Hanford site, building a new education center there. Throughout history, we have sought to understand the great mysteries of the universe. Nothing has captured our collective imaginations and study more than the beauty and wonder of the cosmos. Perhaps this is because, as Carl Sagan said, we are made up of star stuff. And that is a truth the LIGO and Virgo collaborations have helped make even clearer. Your efforts have unlocked another mystery of the universe and raised new questions for us to answer. Thank you again for allowing me to join you today and to IEEE for this most deserved recognition of this historic achievement.
Till recently, the two founding members of LIGO hosting the Virgo detector were the CNRS and the INFN. Recently, we have a new member, and this is the Dutch colleagues from NICEF. So the first founding member that I have the pleasure to introduce is the CNRS, and essentially Antoine Petit. Its president and director general since 2018. He's a professor of exceptional class, and he has a PhD in computer science from the University Paris Diderot, where he specialized in formal methods, mostly based on transition systems.
It's an honor and a real pleasure for me to speak on behalf of CNRS for this IEEE milestone event, which honors a truly exceptional achievement, the detection of gravitational waves. This prestigious international recognition honors significant scientific and technical achievements of the LIGO and Virgo collaborations. Not only did LIGO and Virgo detect gravitational waves, but this scientific achievement is no less than the confirmation of Albert Einstein's 1916 theory of general relativity more than 100 years ago. The signal itself was emitted more than 100 million years ago, and LIGO and Virgo are now able to routinely detect even more distant ones. This is truly impressive science. But the technical achievements are no less impressive. For more than 2 decades, passionate researchers have been working to build and run certainly the most delicate instrument on Earth, gravitational waves antennas. These unbelievable instruments are able to detect variations the size of an atom and smaller to a distance as large as the distance to the sun. This is truly impressive and, for a non-expert like me, beyond my imagination. What is also impressive is the time and patience it took to achieve this. Decades of hard work to build, adjust, and improve the instruments, and then improve them again, during which funding agencies and research organizations had to be convinced to fund these expensive experiments. I think it's worth mentioning here that this discovery would have never been possible without the long-term commitment of these research organizations and of the governments who found them. We are indeed very fortunate that this could be achieved in our lifetime. CNRS joined this effort in 1993 when, following a now famous Fleury report from the name of the particle physicist chairing the committee, recommended that France invest in the detection of gravitational waves using the technique of gravitational waves interferometers. Soon after, the Virgo project was approved by CNRS and INFN. Construction began in 1997 in Pisa, the very site the IEEE milestone plate would be installed. 20 years later, in 2017, Virgo and the two LIGO antennas jointly detected gravitational waves from the merging of neutron stars, and the same year, the Nobel Prize in Physics would be awarded for the discovery of gravitational waves made just 2 years earlier. To finish, let me back up a minute. I am told that gravitational waves come from the collisions of binary neutron stars or of black holes that occurred anywhere from hundreds of millions to nearly 3 billion years ago. We are also told that these events travel through the universe virtually unimpeded and procedure-minute changes as small as 1,000th of a proton diameter in the arm length of these antennas. I can't help but note how extremely amazing all this is. The numbers we hear are either immensely large and immensely small. The events that create the space-time waves are cataclysmic. The objects involved, neutron stars, black holes, are extreme. The energy released tremendous. The space-time distortion that is detected is small. That's why this discovery is so important. It tells us of our galaxy and beyond. Furthermore, it tells us how our universe was millions or billions of years ago. It's also a way to probe inside the stars themselves, and it is a new window into our universe. Thank you, and congratulations again to the teams that have achieved such an impressive discovery.
The second founding member of LIGO, supporting Virgo, is INFN. And I have the pleasure to introduce Antonio Zoccoli, who is the president of INFN since 2019. He made his studies in Bologna, where he became professor in 2003. He was also the director of the INFN section of Bologna, president of the Fondazione Giuseppe Occhialini, and very early became member of the INFN executive board, where he was responsible for high energy particle physics and also scientific computing and large research infrastructures. He was also, for some time, vice president of INFN. He is also an unfailing supporter of the Virgo and LIGO program, and I have enormous pleasure to present him to you.
Once upon a time, this is the starting point of every beautiful tale, and is a good incipit also for our story. Once upon a time, in the year 1916, Albert Einstein postulated for the first time the existence of gravitational wave. 100 years later, in 2016, the first detection of gravitational waves was announced. 1916, 2016, a period of time that must make us think. What is the meaning of the 100 years that have passed since the concept of gravitational wave was introduced by Albert Einstein, until its existence was experimentally proved by our interferometers. It took a century-long journey to realize the discovery that opened a new era in the exploration of our universe, the era of gravitational and multi-messenger astronomy. Well, these 100 years represent above all the importance, when doing science, of having vision, courage, and determination. Vision, because we must be able to imagine and look very far beyond the horizon of our life and of our scientific and technological knowledge to design the future of research. Only in this way we will be able to design and plan the path and the tools necessary to make it possible. Courage, because a scientific undertaking of this importance means accepting an extremely demanding challenge without having a priori certainty of how it will end. Investing in it, therefore, means taking on great responsibility and determination, because it is our most precious ally to face obstacles of a long, bumpy, and not at all obvious path. With vision, determination, and courage, we were able to demonstrate the existence of gravitational waves. After a century of their theoretical prediction, we were able to measure what Einstein believed would never be possible to measure. It took a century, yes, because to do this, we had to design and develop cutting-edge technologies, adopt technologies that did not exist before. We had to produce innovation. The history of science told us the progress is tightly linked to the progress of technology. To reach this goal, we developed a sophisticated system of super attenuator of seismic noises, ultra-high vacuum, very high precision lasers, extremely smooth mirrors, accurate algorithm, and powerful computing system for data analysis. Technologies pushed beyond the imaginable to achieve the finest measure ever. We have designed and developed a cutting-edge solution in all this sector to build our interferometers, frontier technology that is already finding application in our society. A technology, therefore, which does not only the good of the science, but also the well-being of people. LIGO and Virgo interferometers are our pride. And it is with this pride that today we receive the important recognition that the Institute of Electrical and Electronics Engineers has decided to dedicate to the instruments that have made possible one of the most exciting and successful scientific enterprises ever. We therefore thanks IEEE for this recognition. And thanks EGO, the European Gravitational Wave Observatory, and thanks to all those who have had the vision, the courage, and the determination to pursue a dream that has lasted 100 years, leading to success. And I want to address a special thanks as president of the National Institute for Nuclear Physics to one of our best scientists, Adalberto Giazzotto, a visionary, courageous, and tenacious person who has inspired and accompanied the work of gravitational wave community over the last years. Strengthened by our success, we are now ready to take on a new challenge with the Einstein telescope for a third-generation interferometer that can further expand our horizon, our knowledge of the universe, and our technological capabilities. Thank you very much.
Our next speaker is Miriam Lautzen. She is a director of the NWO, which is the Netherlands Organization for Scientific Research, and one of the European funders of the Virgo Observatory in Italy. The NWO also steers the course of Dutch science by managing the country's knowledge infrastructure. Miriam is a past director of the Mesa Plus Institute for Nanotechnology at the University of Twente. She was also chair of the Dutch National Laboratory for Nanotech Research and Development.
Ladies and gentlemen, it's an honor to be here to witness the IEEE Historical Milestone for gravitational wave antennas for Ligo, Ego, and Virgo. As director of the Institute's organization of NWO, the Dutch Research Council, I represent the activities on gravitational waves of the Netherlands. This research is carried out by the National NICAF collaboration that includes our National Institute of Particle and Astroparticle Physics, NICAF, and the activities on 6 Dutch universities. And I must say, your research on gravitational waves, with all the developments of the past few years, is truly impressive. It caught the imagination not only of the scientists directly involved in the research, but also of the general public. Your research provided a completely new window in observing our university and brings deep and significant answers in the exciting journey to the fundamental questions of space and time, our universe, its origin, and its destiny. The challenges of the instrumentation are immense, and like many others, I was particularly astonished when I realized how incredibly tiny these gravitational waves really are. The amplitude was compared to the increase of the level of the IJsselmeer, a big lake according to the Dutch standards of more than 1,000 square kilometers. Its level rises when a single extra drop of water is added. Even then, the gravitational waves we actually measure are smaller by a factor of 10,000. And this is truly mind-boggling. From the Netherlands, we are very proud to be part in this endeavor. NICAF has produced significant instrumentation for Virgo and is, as we speak, involved in various upgrades of the antenna. Students from many universities connected to NICAF are directly exposed to this research and are really looking forward to the next level of more sensitive data in the coming years. Only very recently, NWOI, NICAF, has become a formal member of EGO, strengthening the international collaboration on gravitational wave research in Europe. Our ambitions are high as we foresee a rich and deep future for this research. Together with INFN, NICAF is coordinating the preparation to construct a next-generation gravitational wave antenna, the Einstein telescope. This ambitious project is still in the conception stage, with one scenario that it will be constructed at the border area between the Netherlands, Belgium, and Germany. The coming years will show how realistic these plans really are and if political support can be secured. In the meantime, the Netherlands, Belgium, and Germany have started to construct the ET Pathfinder, an ingenious and fully operational R&D facility to test and optimize the instrumentation for the Einstein telescope, irrespective of its future location. With first detections of gravitational waves, we entered a new era of exciting multi-messenger science. The prospects of this field are so promising that our universities established new research groups, and the gravitational wave group is now the largest at NICAF. But it also works to strengthen ties with industries and small companies to tackle all challenging barriers for new detectors. This brings me back to the reason we are celebrating the recognition of this research by IEEE. It is an achievement that fully fits this research. I congratulate all members of this wonderful Ligo-Virgo collaboration for this well-deserved reward, and I look forward to the continuation of this fascinating story.
Hello, I am Kate Duncan, the 2021 president of IEEE USA. In my day job, I am involved in research and development of magnetic nanoparticles. And now I would like to share with you some thoughts on this extraordinary achievement. LIGO and Virgo are excellent examples of results from making long-term commitments in basic research investment. The National Science Foundation has invested more than $1 billion in LIGO over a 40-year period to confirm Einstein's prediction of gravitational waves of over a century ago. Einstein himself did not believe the measurement of gravitational waves was possible because the technology required to make this measurement was far too advanced for his time. LIGO was a high-risk investment, the largest single effort ever undertaken in the 75-year history of the NSF. The return on that research investment now provides us with a fundamentally new way of looking at our universe. This is truly a monumental physics and engineering accomplishment. The direct measurement of gravitational radiation required an innovative international collaboration applying state-of-the-art multidisciplinary engineering and technology. The confluence of these technologies working together provides LIGO and Virgo with the ability necessary to measure 1/10,000th the width of a proton. That measurement capability enables us to detect some of the most energetic forces that occur in our universe. It is amazing to consider that we can measure gravitational waves produced by the coalescence of two black holes from another galaxy located over 1 billion light years away. The IEEE milestone being dedicated today is in recognition of the extraordinary innovation and collaboration that was required to make Einstein's prediction a reality. I am concerned, however, over the reluctance of making this type of long-term investment in science today. Projects like LIGO and Virgo have always been too big, too risky, and too long-term for private companies to undertake. It falls on the public sector of the international community to support large-scale and long-term projects like LIGO and Virgo. The first LIGO detection simply would not have been possible without the NSF's unwavering support. Policy decision makers must recognize the intrinsic value of long-term basic research investments. We can't build projects like LIGO today using a short-term investment strategy. We must provide the long-term support necessary to make the returns on this type of investment a reality. The potential return on investment in highly speculative research is enormous in terms of what it provides for our future society. This kind of investment is needed to keep our researchers at the forefront of innovation that enables discovery and to disrupt our complacency. As we approach the 1/4 mark of the 21st century, we need to make more of these investments to take on the seemingly impossible problems by applying transformative solutions that allow us to boldly reshape both our knowledge of technology and of the universe. The international array of organizations that made LIGO and Virgo a reality holds a bold vision for scientific research. These scientists and engineers have provided us with an extraordinary example of what we can do when given the time and resources to tackle big projects and big questions. On behalf of the IEEE USA and the 170,000 IEEE members in the United States, I want to thank each and every person who contributed to the success of LIGO and Virgo. You have shown us and our political leaders what a collaboration of brilliant people from around the world can achieve when they are challenged. I look forward to the future accomplishments of this team and others like it. I would now like to introduce our next speaker, Rich Abbott, who is the LIGO Electronics Group Leader. He has overall responsibility for the electronics hardware at the LIGO site in both Hannaford, Washington and Livingston, Louisiana. Rich came to LIGO from the particle physics world over 25 years ago in the capacity of an electronics design engineer. He is an IEEE senior member, and he played an active role in the organization of today's event. He also was gifted with the task of interviewing the 3 winners of the 2017 Nobel Prize in Physics for today's event. Those 3 gentlemen received that distinguished honor for decisive contributions to the LIGO detector and the observation of gravitational waves. Take it away, Rich.
Firstly, a thank you to Kate Duncan, the 2021 IEEE USA President, for the kind introduction, and to the IEEE for the honor of the LIGO Milestone Award. I am Rich Abbott, and it is my sincere pleasure to introduce three gentlemen who have been a source of inspiration and guidance to so many of us within the field of gravitational research and beyond, the recipients of the 2017 Nobel Prize in Physics for the direct detection of gravitational radiation, Drs. Rainer Weiss, or Ray as we call him, Kip Thorne, and Barry Barish. Gentlemen, thank you for being here today.
Thank you.
Thank you.
I have a few questions for the three of you to learn a bit about your personal views on the history leading to the creation of the observatories and to look into the crystal ball to the future of gravitational wave astronomy. So feel free to self-assemble on the answers to these questions. It's watching your interaction that's going to be genuinely fun for us in the audience. So I'll start with the first one. What did you find to be the greatest challenge in LIGO?
People.
I agree with Barry.
We had, well, I mean, it's true, I think, in anything, but we had a very, very large group of very talented people spread around the world that worked on this for a very long time. And that's a complex social environment where different people have different, not just different skills, but different motives and different backgrounds. And I think that's the hardest part. We're pretty good technically. We learn about all that, but we don't get trained as much to do people problems.
Let me answer what Barry said. Is that specific problem that we had was that it was hard for many of us to make the transition from tabletop physics, where you're in charge of all your own world and your own people, to a thing which was much larger than that. And so it had to be organized and into subsystems and had to be organized so it wasn't completely under your control. That was very hard for everybody, but hardest for one of us. His name Ron Drever. And that was, in fact, I think the biggest challenge we had is, as Barry says, was people, but that was the biggest one. And Kip and I and Drever worried that problem for many years.
I would say there was another huge challenge that was equally large, at least equally large, and that was just how far we were when we began. If you go way back, the earliest epoch in the early 1970s, how very far we were technologically away from having the techniques, the technology, for really pulling this off. And I was highly skeptical initially that it could possibly be done because it was so far away. And it was only after long conversations with Ray in the mid-1970s and Vladimir Berginsky in Moscow and others that I really became convinced that there was a chance of pulling it off. And while I had huge respect and confidence for my experimental colleagues, nevertheless, it was a long road to hoe. And the fact that you, my experimental colleagues, were able to pull it off is just a tremendous tribute to your skills and your wisdom.
Thank you. So the next question, the news media has written extensively on the black hole and neutron star mergers, but what are some of the indirect scientific insights made feasible by the detection of gravitational radiation? Those things that we in the public might not find obvious.
Well, the thing that I'm the most enthusiastic about is that in the black hole collision that LIGO has seen, we are for the first time ever in human history observing the behavior of gravity and its associated warped or curved space-time in a situation where the shape of space, the rate of flow of time are changing extremely rapidly. And the processes going on are what we call very nonlinear. This is a whole new domain for observing the warping or curvature of space and time. And it's a regime where we didn't even know the predictions until we had numerical simulations only several years before the observations were made. And the fact that the gravitational waveforms that the LIGO sees agree so beautifully with the computer simulation tells us that the wild behavior of highly warped space-time that general relativity predicts and that we see in the simulation, that it's really happening. So it's a completely different regime for studying the nature of gravity of warped space-time, a regime made possible only through the combination of this superb technology and skills and data analysis skills of LIGO and the computer simulation.
I might add there's some surprises observationally already, and that's something we'd always hoped for. So one thing was, of course, to confirm what Einstein had proposed about gravitational waves. But even black holes, the first thing we've observed, we have an interesting situation that we've observed ones that are heavier than we thought were likely to be in nature because of the fact that the parent stars are unstable. And maybe we've seen ones also that are too light to satisfy what people thought you had to have, how much mass you had to have a black hole. Those aren't confirmed at this point, but I think as experimentalists, observing things in nature that don't fit the pictures that people have is kind of our dream.
Mm-hmm. Oh, let me add to that a little bit. I mean, it's an interesting question you ask. What besides gravitational waves? I mean, the thing is, a lot of the thing we're now going to learn, which we don't know anything about, is where these sources, as Barry points out, come from. And I hope that that's going to be one of the more interesting things for what the science of both astrophysics and cosmology. For example, it might very well be that these black holes might come from primordial things. We don't know that. I mean, that's a nice idea. It may not be true, but we don't know right now where these binaries all come from. We can think of other ways. And the other thing is, I hope that, and Kip has said this over the years in many of his wonderful talks about the field, it's a different field than any of the others in astronomy, in the following sense, that you can look inside of things. You see, these gravitational waves don't seem to scatter, they don't get bothered by anything. So they can go across the whole universe without really changing their character. You can start from one side of the universe that we have, go all the way to the other, and still they come out the same. You can't do that with light. Light gets scattered by everything in the world. And so here is an idea that you might be able to look inside of things that you have never been able to do. And I think one of the things we might find out, for example, is what's went on in the earliest universe. We might find out what really goes on in a supernova. These are things, I guess, in your questions later, but they're directly those things that might very well be new for us.
So my next question, the importance of international collaboration to the next generation of detectors. And traditionally, this has been an effort that the machines that were built in the US have an international aspect to it, but how important do you think that's going to be in the future, these larger machines and the distribution of detectors?
Rich, it's critical. I mean, in fact, we already have much better information about our sources because Virgo is on the air as well, as besides the two LIGO detectors. And I hope Kaga, when they get sensitive enough, will add to this. We can't point these detectors. That's the important thing. There's no way to take and aim the detector at a source like you do with a telescope. They're sensitive to pretty much omnidirectional. It's quite a little bit of an exaggeration, but it's almost omnidirectional. So how do we know where these sources are in the sky? We do it by timing. In other words, the first source we ever saw was a binary black hole, which made a signal that came to Louisiana, and then it went through the Earth and came up again in Pacific Northwest. That's how we knew that was somewhere in the southern sky. But we had no idea about where the thing is otherwise. So it's very important to use the Earth as a way to get different times, many detectors, different times. And why is that important? Because you'll learn so much more about what's going on if you can then take that information, where the source is, and tell a real astronomer, you know, classic astronomer, go look over there. And if they see something, that adds dramatic information to the. It's called Multi Messenger Astronomy. It's a big new field for the NSF.
So that's from the technical standpoint. I think from the standpoint of doing very risky, challenging science, if all the expertise is not in one place in the world, it's not in the US. And so if you just take LIGO now, our expertise is leans very heavily on expertise and contributions that came from Scotland, Australia, Germany, and so forth. And that's only going to be more so. I mentioned particle accelerators. It's again, there's no way to step back. The expertise is around the world. The people that know the most aren't necessarily in one country, certainly not in the US. And so both in terms of a group of people being able to do a challenging technical and scientific project, and for LIGO, or for gravitational waves, the additional fact that you want to spread the detectors around the world. It's completely a one-way street, I think.
And this international aspect has been the case from the very beginning, going way back to the 1970s, when Ray originally conceived these types of gravitational wave detectors. A group in Germany led by Heinz Billings jumped right in and started developing these detectors there. And the technological developments in there and in Glasgow at MIT and later at Caltech, they fed on each other with extensive interaction between the various groups. And so the foundation on which LIGO was built, as LIGO started to move forward under Barry's leadership, was really an international foundation from the very beginning.
Interesting, thank you. So next question is a little more pie in the sky, but let me ask you anyway. We've seen the mergers of neutron stars and black holes. What events are you hoping for next?
I want to see a black hole tear a neutron star apart. We'll see that in detail and see the gravitational waves that are coming off from that neutron star as its guts are spilled out in the surrounding universe.
Graphic. Great.
Well, it'd be nice to see a supernova. Now, that was the initial mantra. Turned out that in the early days, we thought that would be the only source. And then they became a very disappointing source because we suddenly realized the neutrinos that Barry was studying would slow down the explosion, would make much less gravitational waves than what the initial thought was. But still, it's a fascinating source. Why? Because what really goes on, you see with gravitational waves, as I said before, you can actually look into what the supernovas do. You can look at the star that actually is exploding. And nothing's going to stop that gravitational wave from coming out of that region inside where the thing is really the dynamics that goes on in the supernova will be exposed for the first time. It's going to be fascinating. I bet we don't get very many of these, you know, and they have to be, unfortunately, most likely in our galaxy. So you got to wait a while. But let's hope we're all on the air when it happens.
Oh, yeah.
And I'll pick something else, which just shows this can go in many, many directions. I think next might be, that's really interesting, might be continuous sources. That is a spinning neutron star. And it has the nice feature compared to these other ones that you can keep studying it. We can get, once we find one, we can keep studying it with better observations and so forth, because it's there. It's not just something that happened in a transient way. And we don't know very much about what this compact nuclear system is going to be like. And so the science should be pretty exciting, I think.
That is exciting. Great.
But I think of all the things that we might see, I think the thing that will be most exciting is something we didn't predict, something we had no idea was coming. And
prize gift.
And this is from the very beginning when we first started thinking about LIGO. this has been my dream and my expectation. And so we will see, but I'm pretty sure it will come. And it could revolutionize our understanding of the universe when that happens.
Excellent.
Kip's been saying that as long as I've known him.
So the last and least technical question and most philosophical, how has this long ride to where we are today changed your lives?
Really?
That's a broad one, I know, but you can pick the top one. I don't know, your choice.
Well, I've gotten older. I like to think a little bit wiser.
Good.
I've come to appreciate my colleagues enormously and appreciate and understand the power of collaboration, the critical roles played by people who have very different skills they bring to this. But looking in from another point of view, this has provided enormously increased opportunities to inspire young people about science. In LIGOs, and what it is saying is a truly inspirational story, the history of it, and the science that is coming out is inspirational. And I think inspiring young people about science is one of the most important things that we can do as scientists.
No, I have a much more pedestrian view yet. But I mean, there was one unpleasant part of this whole thing you heard about at the beginning, the problems with making the change in looking at the way you do the work. That was the only one. I think for the rest of my whole life on this thing, it's always been that it's been a lot of fun to work on. Look, the fun comes about by building circuits or by machining things in the shop, or you're going out to the site to commission and it actually works, or you're working on a puzzle and suddenly you find the answer. These are wonderful things to imagine. It's a privilege to be able to do that.
It sure is.
And so the thing is that, you know, and having good colleagues is very important. So just what Kip said and Barry also. So I don't know, I don't want to draw any deep lessons. I think that the one I always say to people is that if it's not fun, don't do it. And you'll never do it. You'll never do anything. You'll just always think of another thing to do better. You know, that's.
Well, it's been a real pleasure speaking with you. That's all the questions I have for today. But I'd like to tell you, on behalf of all of us here today, please accept our gratitude for your work and for being here with us today and sharing your insights. Thank you very much, gentlemen.
Thank you.
Thank you. Thank you.
Real pleasure. Thank you.
Okay.
Composed of two 4-kilometer laser interferometers, housed in immense vacuum envelopes, and separated by 3,000 kilometers, LIGO is engineered to detect tiny vibrations in spacetime, predicted by Einstein, and produced in the most powerful astrophysical events known to human beings. The two NSF-funded LIGO detectors, LIGO Hanford in Washington and LIGO Livingston in Louisiana, were designed as discovery machines, searching for the force carry of gravity predicted by Einstein in 1916, gravitational waves. Virgo operates a 3-kilometer detector in Cascina, Italy, yielding a network of 3 gravitational wave detectors, which operate in observation runs lasting many months. All components of the detectors are fabricated to exacting standards to achieve the required sensitivity: optics, lasers, isolation and suspension systems, control and readout electronics. The integrated observatory relies on exquisite design and componentry. Mirrors must be isolated from ground motion with elaborate suspension systems. The motions of optics are suppressed by a factor of 10 billion times compared to that of the ground on which they're suspended.
At the LIGO Hanford Observatory, we operate one of the world's largest vacuum systems. The scale is 10 million liters in volume. It has 2 beam tubes that span 4 kilometers in length, 1.2 meters in diameter, and the operating pressure is a nanotorr, which is comparable to the pressure on the surface of the moon.
After a decade of R&D, the fabrication, assembly, installation, and testing of advanced LIGO components took several years. LIGO's precision measurement required use of cutting-edge electrical, materials, optical, mechanical, vacuum, controls, and IT engineering. Most of the critical parts operate inside the vacuum envelope, and so they must be assembled in clean rooms and be free of contaminating substances and dust. Sensing and actuation instrumentation allows precise and configurable servo control of optics, lasers, and of mechanical motion and alignment.
We have hundreds of control loops in a single chamber just to damp it from ground motion seismically. Has 12 control loops, monitoring ground motion and canceling that out. Then we have control loops to control the optics that hang from that suspension, as well as what we call our length sense and control, or interferometer sense and control, where we then lock cavities. Those have their own control loops.
The instruments can measure length changes between the 4-kilometer arms of around a 10,000th the diameter of a proton. Multi-input, multi-output digital signal processing is carried out in LIGO-designed processor code, overseen by supervisory guardians and configured for low noise and stability by scientists, engineers, and students. LIGO's main laser is in the near-infrared, ideal for low-loss optics and optoelectronics, but some sensing and control acquisition relies on green light, seen here as these systems are aligned and commissioned. Since LIGO was initially conceived, our prospects for success benefited greatly from advances in the engineering state-of-the-art. We are grateful to the IEEE members and our staff and elsewhere whose innovations have enabled these and other precision astrophysical observations.
I wake up every day knowing that I'm going to be working with this group of people that propel me to ask questions every day, that invigorate me to learn something.
At LIGO Livingston, the Science Education Center sees 10,000 visitors per year for a hands-on learning experience about the science and technology of LIGO. Soon, visitors will do the same at Hanford's LIGO Exploration Center under construction. These students represent the future. They are the engineers, the scientists, and the technicians who will form high-tech companies and construct future observatories to improve our world and reveal the hidden in our universe.
We are pleased to have Dr. Sherry Nguyen in our program. She has worked in computer architecture at IBM, is a longtime IEEE officer, has served as United States National Commissioner to UNESCO, and is founder and president of UNESCO's Washington State Senator. Dr. Nguyen has been recognized by the New York Times as a top woman entrepreneur and by Japan Asahi News as a prominent Asian professional woman. We thank Dr. Nguyen for facilitating Washington State Governor Jay Inslee's inclusion in our program.
Good morning. It is my great honor to introduce the Governor of Washington State, Honorable Jay Inslee. After serving in the United States House of Representatives, Inslee has led Washington State as the governor since 2013. His dedication and leadership had brought Washington State ranked as the highest growth in economy, GDP, and STEM workers, as well as the best place for business. Governor Inslee also led Washington State, ranked top 2 in innovation. Most of all, Governor Inslee believed and provided funding for LIGO. Let us all welcome Honorable Governor Jay Inslee.
Thank you, Sherry, for that introduction. I'm really excited to join you and recognize the amazing scientific breakthroughs achieved by the team operating LIGO Virgo, the gravitational wave detection facilities here in Washington State and in Louisiana and Italy. This work has already achieved international recognition, as you know, in 2017, when professors Barish, Thorne, and Weiss shared the Nobel Prize for Physics in their contribution to the groundbreaking discovery of gravitational waves. And today, we honor the entire LIGO Virgo team with a prestigious Institute of Electrical and Electronics Engineers Milestone in Electrical Engineering and Computing Award. For well over 50 years, scientists and engineers have sought to verify Einstein's prediction that space itself is distorted by collisions of massive astrophysical bodies, such as black holes. And the LIGO Virgo team did just that, detecting multiple collisions of black holes and neutron stars, confirming Einstein's prediction, and establishing a new astronomical observatory for future exciting discoveries. I'm especially proud, of course, that Washington State played an important role, hosting one of the 3 laser interferometer gravitational wave observatories at Hanford, and funding it in part. I played some role in that when I served in Congress. About 40 scientists, engineers, and other support personnel call southeastern Washington home as they work to further this critically important research. And I'm thankful also for the work they've done of spreading the education of science in my state and other places. So good luck. Thanks for this incredible achievement. And let's keep searching for truth.
Thank you for providing me the opportunity to represent the great state of Louisiana in this milestone dedication. The accomplishments that we are recognizing today are a testament to the hard work that was made by scientists and engineers from around the world. As you know, Louisiana State University donated the LIGO Livingston site some 30 years ago. Since that investment, the National Scientist Foundation has provided more than $1 billion in funding. We have businesses from around the state that have supported this effort. And as a result, LIGO's impact on our local economy is significant. I would like to thank the IEEE members who are making contributions around Louisiana and the many others at LSU and beyond who are making an impact using their scientific, mathematical, and engineering skills. These students will become our future leaders and entrepreneurs leading our next generation. Thank you, and I'm proud of all of you for your efforts in helping Louisiana make strides in the scientific community.
I really thank the scientific collaboration LIGO and Virgo and the European Gravitational Observatory, EGO, that give me the opportunity to join this celebration, and I sincerely congratulate you for such an important acknowledgement as the IEEE milestone dedication to gravitational wave antennas Virgo and LIGOs. It's clear that the fact that the scientific and technological infrastructure of Virgo and of the European Gravitational Observatory are included in this path market the most important goals of human progress. It's fundamental recognition not only of the revolutionary contribution of Virgo's and LIGO's discoveries, but also of the extraordinary and pioneering technologies which made them possible. I know that this technological and innovation could be soon also be applied in many and diverse fields. The study of air quarters, the sea and the climate, smart grids, big data, robotics, and will have in this way also a greater impact of society. Congratulations again, and which for all other extraordinary similar success in the future that surely will arrive.
Ladies and gentlemen, good morning, good evening. I am Vincenzo Piuri, former Vice President of the IEEE Technical Activities. I am very glad and honored to introduce you Professor Antonio Luque, Director of the IEEE Region 8, the region in which the Virgo system have been conceived, designed, realized, and installed, where one of the measurement sets of the gravitational waves have been performed.
Hello, everyone. I'm happy to be here at this milestone dedication representing IEEE in Europe, Middle East, and Africa. This milestone honors the technical achievement that led to the experimental confirmation of one of the most important theories in modern physics. But it also highlights the value of international collaboration in research. In this particular case, the distance between the interferometers plays an important role in the physics and the confirmation of the experiments. And the design of the LIGO and Virgo stations had to be considered together initially, also with other detectors in Germany and Japan. That is why this milestone also highlights the birth of Multi Messenger Astronomy. But there are many other examples where international collaboration is not a requirement of the experiment itself, but a necessity of the way that modern science is done. We are all aware of the most impactful development coming from science and technology in the current environment, which is the availability of several COVID vaccines in less than 1 year, giving us hopes of ending with the current pandemic, thanks again in big part to international research collaboration. According to UNESCO, 1 in 3 scientific articles published in the last years were co-signed by an international collaborator. This is up from 1 in 5 1 decade ago. More impressive is the fact that more than 85% of articles in low-income countries were the result of international collaboration, or 40% in low to mid-income ones. To me, this highlights the importance that developing countries invest into international science for the future. It should also be noted that a big part of this is due to affordable access to scientific publications in these countries, and the role that open science and experiment reproducibility play will only increase. In the same report about international science, UNESCO also mentions that mercantilism characterizes much of national policy making in science, technology, and innovation these days. Everyone wishes to attract foreign research centers and skilled professionals, but few are prepared to discuss frameworks for facilitating this cross-border movement. It is perhaps time that we, as scientists and technologists, push for a return to research that benefits everyone equally, regardless of the original income. I'm proud to represent an organization that strives for that. That is today recognizing international collaboration in basic research as a milestone, and whose aim is advancing technology for the benefit of humanity. Thank you.
I am Giovanni Losurdo, spokesperson of the Virgo collaboration, and I have the pleasure to introduce Professor Nariman, one of the pioneers of gravitational waves research in Europe. Since 1982, with Alain Brière, she gave crucial contributions to technological breakthroughs which have later made observation of gravitational waves possible. Laser stabilization, YAG lasers, injection locking, demonstration of power recycling. Later, for many years, she has been the director of the Artemis Lab and the leader of the Virgo group based at Nice.
So, hi everybody. I will retell the story of the Virgo project along with my colleague Jean-Yves Vinet, and my talk will be on some of the experimental parts. When we started working at the detection of gravitational waves in the early 80s, it looked clear that the proposal by Ray Weiss on the kilometric interferometer could provide a very high sensitive detector. However, our current technology was far from satisfying many requirements. The signal to be detected, those phase variations of light waves, were not well known, but certainly very weak, and we faced two problems: how to measure extremely small phase shifts of the light beam, and how to isolate the interferometer from the perturbation of the environment, which come from seismic, thermal, and electromagnetic fluctuations. We worked on solving the first problems, while Adalberto Giazzotto and his team in Pisa were working independently at the seismic isolation. They designed a multi-stage pendulum called super attenuator, which provides excellent results at very low frequencies. In France, we have a small team, 3 physicists and an electronics engineer. We decided to start working towards full-size components rather than focus on the sensitivity of small prototype detectors. We first developed the low-power infrared laser, the so-called neodymium YAG, which were very promising concerning reliability and evolution towards high power. Together with advanced electronics, very fast and low noise to reach record frequency stability and power stability. So within a few years, this choice was validated and adopted by all the other teams. I should mention that part of this work was done in collaboration with Ray's young students, David Shoemaker and Peter Fritschel, who are now prominent members of the LIGO collaboration. Since then, laser power would increase from 100 milliwatts to 100 watts, increasing then the sensitivity of the interferometer by dozens of times and the number of detectable sources by some thousands. In parallel, we developed a program for modeling and computing the requirements of the interferometer to put specifications on the mirror parameters, the alignment, and the geometry of a laser beam. We realized that the requirements concerning the mirror quality were larger than what any manufacturer of optical components could develop. So in the 90s, we decided to build our own mirror research lab, which today stands as a full-fledged mirror facility. This lab in Lyon, which is the basis of fruitful collaborations with advanced European and American optics company, and with LIGO, is now the sole facility in the world able to deliver adequate mirrors for all the advanced gravitational wave detectors. I'm grateful to CNRS to support this beautiful experiment since the beginning, and I would like to thank all my early collaborators. Thank you.
Let me now introduce Professor Jean-Yves Vinet. He has given remarkable theoretical contributions to the understanding of how gravitational wave interferometric detectors work and can be optimized, writing relevant papers on optics, thermal noise, scatter light, and developing numerical optical simulation. Moreover, he has been the spokesperson of the Virgo collaboration between 2011 and 2014.
The first detection of a gravitational wave in year 2015 was celebrated as a worldwide event. LIGO and Virgo's 20 years of theoretical and technological developments led to this great achievement, and it was good and necessary. But the first detection had been done by 2 American instruments, even though preliminary technological efforts, the waveform predictions, the data processing, and more generally the physical principles had been widely discussed, and the results shared between the 2 collaborations during a number of years, even if the first official published detection was signed by our 2 collaborations after the agreement confirmed in 2014. This is why I was delighted after the first detection of a binary neutron star coalescence in August 2017 by our 3 interferometers simultaneously, the 2 LIGOs and Virgo, and its electromagnetic counterpart in the NASA and ESA satellites. This was not the first common detection, but the first one, including all the astronomy and astrophysics communities and Virgo. I had then kind of a flashback, and I remembered all the challenges we had to address from the very beginning of this long adventure. I remembered the efforts of my late friend Philippe Tourinck in the 70s to create a gravitational wave community in France. In France, at that time, gravitation was a domain of pure theoretical physics, illustrated by figures like, for instance, André Lichnerovitz and Achille Papapetrou, former professor for me. And I remember the first meeting at Institut Henri Poincaré, which was the temple of general relativity and pure theory in France. This meeting aiming to insert the French scientists, theorists, as well as applied physicists and quantum opticians into this new field for us, experimental gravitation. I remember the long efforts of Alain Briet for obtaining the support of our institutions, the 4 physics institutes of CNRS, skeptic at the beginning, surprisingly. Finally, the Institute for Nuclear and Particle Physics agreed to support our works regarding its resources in manpower, engineers, technicians, and so on, and its culture of large instruments developed at CERN. I remember the friendly collaboration with Italian colleagues led by Adalberto Giasotto after 1985 to finally reach a French-Italian project in 1987. But unfortunately, to my opinion, it was politically impossible to make it evolve towards a full European project. One important point was the choice of a direct full-size approach of interferometry, avoiding loss of time on small-size prototypes problematics. I remember the efforts to develop special technology at Orsay and Pisa for long baseline interferometers, frequency-stabilized solid lasers at Orsay, seismic isolation by the famous super attenuators at Pisa, technology which are now widely spread. I remember the struggle of Alain and Adalberto to get at the end the site of Virgo from a number of land parcels on the ground. After more than 6 years of constructions, we could not have known that after 10 more years of issues and solutions, a clear and complete success would suddenly happen. I then realized that during my lifetime, I would be present for the beginning of Multi Messenger Astronomy.
Takaki Kageta is the president of the Science Council of Japan since October 2020. But he is mostly known for his Nobel Prize of Physics of 2015, a Nobel Prize he shared with Arthur MacDonald on neutrino oscillations. As of 2017, he is one of the principal investigators at the Institute for the Physics and Mathematics of the University of Tokyo, and he is also, of course, director of the Institute of Cosmic Ray Research, again, in Tokyo. But understanding part of the cosmic neutrino messenger nature was not sufficient for Takaki, as I know him. So he also initiated the effort for the Japanese gravitational wave detector at Kamioka called KAGRA. He's currently the principal investigator and will talk to us about KAGRA and also some of his ideas about the future of the gravitational wave field.
Hello, everyone. First, I'd like to congratulate to the LIGO and Virgo colleagues for the IEEE milestone. Our colleagues in LIGO and Virgo have developed extremely sensitive laser interferometers and opened a new kind of astronomy, namely gravitational wave astronomy. Indeed, recalling the history of astronomy, we find that whenever a new method or instrument of observing the universe was developed, discovery of new phenomena soon followed. In many cases, these discoveries revolutionized our view of the universe. Clearly, the discovery of gravitational waves is one of them. For example, the observations of binary black hole mergers have told us unexpectedly that there are black holes heavier than what many star formation theories predicted. The observation of a binary neutron star merger in 2017 was extremely exciting. The follow-up optical observations have even told us that heavy metals such as gold were produced in that merger. Now, gravitational wave astronomy is just starting. More discoveries await us, and the global gravitational wave community is preparing for them. In fact, one very important role of gravitational wave observation is to tell the optical telescopes the location of the gravitational wave events in the sky for the detailed follow-up studies. The accurate pointing of these events is very important. For the most accurate pointing, global collaboration of the gravitational wave detectors is paramount because it is made possible only by comparing the signal arrival time from each detector. If the detectors are separated in the location, the accuracy can be improved. KAGRA is located in Japan, far from the LIGO and Virgo interferometers. Because of its location, it can play an important role in the global collaboration of gravitational wave detectors. Finally, we predict that more sensitive interferometers will be constructed in the future, which will advance the gravitational wave astronomy further. In order to achieve higher sensitivity, we have to reduce various noises, including thermal noise. One simple solution is to cool down the mirrors. KAGRA uses the cryogenic technology to reduce the thermal noise. We hope that the cryogenic technology developed in KAGRA will be an important contribution to the future gravitational wave interferometers. We are all excited with the new gravitational wave astronomy. Once again, congratulations to the LIGO and Virgo colleagues for this amazing achievement. Thank you.
Dr. David Reitzy is the Executive Director of the LIGO Laboratory at Caltech, where he oversees a 180-person scientific and engineering staff that built and operates the LIGO observatories in Hanford and Livingston. He also holds concurrent positions as a research professor at Caltech and as a professor of physics at the University of Florida. David is distinguished as a fellow of 3 organizations: the American Association for the Advancement of Science, the Optical Society of America, and the American Physical Society. He was the principal investigator for each of the 4 major phases of LIGO funding from the National Science Foundation. Dr. Reitzy previously served as spokesperson of the LIGO Scientific Collaboration, a group of 1,200 scientists and engineers carrying out the LIGO science program.
Thank you very much, Brian. I have the honor of providing a few closing remarks for the wonderful recognition to LIGO and Virgo by the IEEE. First, I want to express my profound gratitude on behalf of the LIGO Laboratory for IEEE's Milestone Award for the invention of the gravitational wave antenna, which has opened this wondrous new window on the universe. Since 2015, when the first binary black hole merger was discovered, LIGO and Virgo have detected more than 50 gravitational wave events. In fact, we can now detect a gravitational wave event on average about once a week. When our current upgrade program is complete and LIGO and Virgo go back online in 2022, we may be able to push that up to detections of events once every 2 or 3 days. What was once thought impossible by some and challenging by all is now almost routine. But of course, it really isn't routine at all. The LIGO and Virgo interferometers are among the world's most complex and precise scientific measuring devices ever devised and constructed, made possible not only by an understanding of subtle and complex nature of gravity described by Einstein's general theory of relativity, but also by the sustained effort to design, build, test, redesign, rebuild, and then retest the systems and subsystems of these complex interferometers, and then do that again and again and again to achieve the unprecedented sensitivity that we now have. That's engineering, and without it, LIGO and Virgo could not have accomplished what we have. I'd like to note this recognition accorded by the IEEE is also given to the thousands of scientists and engineers who have, over the past many years, dedicated their professional lives to this seemingly quixotic endeavor. I want to quote George Carruthers, a black astrophysicist who designed the first telescope that went to the moon on Apollo 16 and recently passed away. He was asked once by a journalist whether he had any hobbies. He replied, "Hobbies? The projects we have here are so varied that it's hardly necessary to have a hobby." I know that's true for myself, and I suspect it may be true for many of us who've worked on LIGO and Virgo over these past many years. This award is also given in recognition of the important role that fundamental research and its intimate connectivity to society at large. The US's National Science Foundation, France's CNRS, and Italy's INFN made a bold decision in the 1980s and 1990s to fund LIGO and Virgo, in spite of some very real concerns about the possibility for failure. They've managed to sustain that commitment until now, and we hope they continue to do so going forward. The benefits to society are not only about discovering new things about our universe, but also about inspiring curiosity and awe in people who
So what I love about IEEE is that it really allows the convening of people of like minds over interesting domains to come together.
I think I've been able to successfully use IEEE USA to position and leverage myself to be in the cutting edge in my industry.
I remember growing up, I used to always like to be creative, and I wasn't necessarily the best painter or the best person at drawing, but I loved art because I was creating something. And engineering really gave me that toolbox of knowledge to solve bigger and more exciting problems.
I've traveled all over getting to know friends at IEEE. We've got a great network. Sometimes when we take apart a new gizmo, we don't understand something or we need to find an expert on acoustics or signal engineering or antenna design. And I've got a group of friends that I've met through the years at IEEE conferences, and it's really fantastic to be able to call up the right expert at the right moment.
Without IEEE, I don't think I would have the network that I have. What IEEE enables is this cross-pollination of generations of roboticists, those that are older to those that are younger.
One of the other things that I get really excited about outside of the work is sharing my knowledge and my excitement with other people. One of the ways that volunteering has really helped me to give back was to connect with people who are where I was when I started my career.
I really think paying it forward and being able to help another person achieve their dreams in engineering is something that really is fulfilling for me to do.
Students and the younger generation, they need to see themselves as the future. So as engineers, we need to show them that this is possible, that they too can be engineers.
I remember handing a kid an iPod and saying, "Hey, do you want to take this apart?" And he looked at me like I was crazy. And I said, "No, it's okay. You can take it apart." And his eyes lit up. He was so excited because every single adult his entire life has been telling him, "Don't take that apart." And I was the first one that gave him permission. And he sat there for an hour taking this iPod apart and putting it back together. That's how we're going to get the next generation of innovation that we need. That's how we're going to build a sustainable electronics industry. It starts with the kids, and we have to get them excited about tinkering.
I've been fortunate enough to volunteer with IEEE and IEEE USA, enabling me to attend conferences where the best part about it is I get to meet people inside and outside of what I do. Meet with them, network with them, understand some of their challenges, and think about ideas that are completely outside of the box. And I get to share and disseminate that information and really make a contribution to my career.
IEEE USA has given me a competitive edge because of their support system. It is so much easier doing something and being out of your comfort zone when you have someone there saying, "You got this."
We need more engineers in the world. Engineers make the world better. They're designing the systems that keep the world working.
Now, the reason why I keep on renewing my membership with IEEE today is I feel a sense of belonging within IEEE.
This isn't just an organization I'm a part of. This is a family.
I've got buddies that I've met at IEEE conferences that will be lifelong friends. We need more engineers, and IEEE is leading the way to make that happen.
I want everyone to think like an engineer and be an engineer, because engineers, we solve problems and we make the world a better place.
IEEE is all about a sense of community.
And having an organization like IEEE USA being there, cheering me on, supporting me, has really made me want to be the best engineer I could be.
IEEE USA is my competitive edge.
(1972–1989). Initially developed from 1972 to 1989, the gravitational wave antenna enabled detection of ripples in space-time propagating at the speed of light, as predicted by Albert Einstein's 1916 theory of general relativity. Construction of the Virgo Gravitational Wave Observatory commenced in 1997. In 2017, Virgo and two antennas located in the USA launched the era of multi-messenger astronomy with the coordinated detection of gravitational waves from a binary neutron-star merger. February 2021. 10.
Let's wait a second. Come down.
Cominciamo.
Let's wait.
Raffaele, anche tu, sì. Allora, e Francesco? Non vedo le... Cominciamo?
Okay. A short speech from Giovanni.
You want to say something?
Now?
Yes, if you want.
So we take this plate as a commitment to continue pursuing this extraordinary adventure of science and knowledge and to achieve new milestones in the very next future. Thank you, everybody.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Il nome dei buchi neri, la coperta della targa era nera.
Sì. Grazie a tutti di essere qui con noi, è veramente un grande onore di aver fatto il viaggio a questi tempi difficili.
Today, we are excited to introduce one of Divi's most amazing new features ever. It's called Scroll Effects, and it allows you to create advanced animations and transitions that react to your visitors as they scroll up and down the page. Any element can be animated using a combination of effects, and creating advanced animations is easy thanks to our brand new Scroll Effects UI that streamlines the complexity of web-based animations and makes them accessible to anyone. Just click to add an effect and it works beautifully. Then fine-tune the animation using simple controls. Any element can now be animated using a combination of scale, rotation, horizontal and vertical motion, opacity, and blur effects that transition based on the direction and speed that a visitor scrolls. You control the magnitude of each effect at different points during the animation, and then Divi takes care of the rest, creating beautiful transitions as those elements enter and move through your visitor's view. Create simple animations that add subtle depth and sophistication, or combine effects and animate multiple elements to create spectacular explosions of activity that will blow your visitors away.
Messi to the net! Mamma mia! Lionel again makes the impossible the predictable!
One little genius is the difference. I mean, today he's just been a genius.
Just when you think you've worked out his genius, he'll then do something else completely different.
First time in. Oh, lovely
genius.
step over from Messi, and there's green.